Okay, day 3, special right triangles. A couple minutes of review before we get into the new stuff. Got to talk about squaring things and taking the square root of things because we're going to use that a lot in the rest of this chapter. And I know most of you know it, but just bear with me as I kind of go through these examples. Okay, first thing, if I square something, if I say I'm going to take a number and square it, that just means I'm multiplying it by itself. So this first example I have here for you, if I say 3 squared, what I'm actually saying is 3 times 3, right? 3 times itself, right? And so 3 squared would just be 3 times 3, which is 9. Same thing with 21. If I say 21 squared, what I'm saying is 21 times 21. And a mistake some people make is they see 21 with that little 2 up there, and they think it means 21 times 2, but that is not what it's saying. It's saying take 21 to the second power, which means 21 times 21, and that's going to equal 441. Okay, so what I want you to do is pause the video, make sure you know how to do this on your calculator. Okay, so if you don't know how to square something, just call me over and I'll show you how to do it either today or tomorrow. So try to do 29 squared. All right, so this depends a little bit on which calculator you're using. The one that I'm using on my computer here looks like this. If I want to know what 29 squared is, usually there's going to be some sort of x squared key on your calculator, and so you would just hit that. And so 29 squared would be 841. Like I said, usually there's some sort of x squared key on whatever calculator you're going to be using. If it's one of the yellow or blue ones in the classroom, I know they have an x squared key. On your cell phone, you might have to turn your phone sideways to get the x squared key to show up, but either way, it should be on there somewhere. Okay, that's if we want to square something. If I want to take the square root of something, I'm basically just doing the opposite. All right, so the second thing we got to review today is taking the square root of a number. Instead of taking a number and multiplying it by itself, when I ask about square roots, what I'm actually saying is, what number do I square to get the number I'm looking at? So if I use 25, if I say what's the square root of 25, what I'm saying is, what number do I have to square to get 25? What number times itself would give me 25? Right? So if I use 81 as a second example, just to go back up to 25, the square root of 25 would be 5. And I know most of you guys would know that just by looking at it. Same thing with 81. If I have the square root of 81, what I'm asking is what number times itself gives me 81, and that would be 9. And these are all things you can find in your calculator. Make sure you know how to do that by seeing if you can figure out what the square root of 144 is. So pause the video, find the square root of 144, write it in this blank. If you don't know how to do it, make sure you ask me. Okay, so if I want to know the square root of something, usually there's going to be a button like this on your calculator. And I know on the yellow calculators that you're using in class, you have to hit second function first, find the x squared key. Basically, you want that, then you're going to enter your number. Oops. There we go. Square root of 144 is 12. Okay, next thing to review. And this one's kind of tricky for some people to process, but it makes sense if you stop and think about it for a minute. Okay, if I square the square root of a number, those two things just basically cancel each other out and just leave me with the number. So for example, if I take the square root of 10, which is just this part right here, and then I square it, which is this part right here, the square root and the square cancel each other out, leaving me with 10. And I'll go through why that is. If I take the square root of 10 and square it, that means I'm multiplying the square root of 10 by the square root of 10, which is what I have right here. When I multiply two radicals, the part on the inside, I don't know why I have 2 of those here, the radicand, the part under the radical just gets, you can put them under the same radical. 10 times 10 is 100, the square root of 100 is 10. So again, the idea is, if I have a number, I could do 8. If I have the square root of 8, and then I square it, the radical and the exponent just cancel each other out, leaving me with just the number. Okay. Last thing for review today. I never want to leave a square root term in the denominator or the bottom of a fraction, right? So if I start with something like let's say I have 3 over the square root of 2. I never want to leave an answer in that form. Okay, here's how you get rid of the radical in the denominator. It's pretty simple, really. You just multiply, you just basically square the denominator, right? But if I square the denominator of a fraction, I have to multiply the numerator of the fraction by the same thing. Okay, so here's what happens. On the top, I'm just going to have 3 times the square root of 2. As we learned in review point 3 up here, if I square the square root of something, it just leaves me with that number. Okay, so this looks more complicated than this, but that's the proper way to end or to sort of answer a problem. Okay, enough review. New stuff now. Let's say I have this isosceles triangle over here. Right? And I know it's isosceles because, well, I have 2 pieces of information that tell me that. First thing I have here is an L and an L, basically saying that this side length right here is the same as this side length right here. The other thing I'm being told just in the picture is that that angle and that angle are the same. And so an isosceles triangle is a triangle where 2 sides are the same. 2 of the 3 sides are exactly the same. The other thing about isosceles triangles is that the 2 base angles are the same. Right? So think back to the fall if you can. I have these 2 sides that are the same. The other side, the side that is not the same, is called the base, and the 2 angles along the base are the same. If I have a situation like this, I have an isosceles triangle. Okay, so this triangle is isosceles because the base angles are the same, and also the legs are the same. Okay, so I'm calling these L for legs. I don't know what number they're equal to yet. I just know that they're the same. Whatever number this one stands for is the same as what this stands for. And then the base is actually going to be the hypotenuse. If I have an isosceles triangle where the 2 base angles are both 45 degrees. All right, so I have this isosceles triangle. The base angles are 45 degrees. This is a special right triangle. The reason it's special is because we know something about how it works. We know that if I wanted to sort of use a formula to figure out one of these 3 sides, I could use this one, the one we've been using for about a week now, a squared plus b squared equals c squared. All I did to get from there to here is rather than calling this leg A and this leg B, I'm just going to call them both L, right? I know that they're the same, so I can use the same variable to represent them. And then instead of c squared, I'm just going to call it h for hypotenuse squared. Okay, now if I want to combine some like terms and kind of simplify this equation, the only thing I can do right now is I can say, well, if I have L squared and another L squared, what I actually have is 2L squared equal to h squared. And let's say I want to know exactly what the hypotenuse is. I just want to know what the hypotenuse is. I don't want to know what h squared is. I just want to know what h is. Well, what I'd have to do is take the square root of that. If I take the square root of the right side of the equation, I have to do the same on the left. Okay, so I'm going to flip-flop this around. The square root of h squared is just h. On the right side, it's a little bit more complicated. What I would have is the square root of 2 times the square root of L squared. So moving down, I can't really do anything with the square root of 2. I mean, I could turn it into a decimal if I want, which I'll do in a minute, but for now I'm just going to leave it as the square root of 2. But I can do something with the square root of L squared. That would just be L. Okay, so what ends up happening is that h, or the hypotenuse, in a triangle that's 45, 45, 90, the hypotenuse is always going to be equal to L times the square root of 2. L meaning the length of one of the 2 legs. So if I have a triangle and it's 45, 45, 90, and let's say the legs are 8, and I want to know what the hypotenuse is, I don't have to even use the Pythagorean theorem. What I know is that the hypotenuse is just equal to the legs times the square root of 2. So without even doing a squared plus b squared equals c squared, the reason 45, 45, 90 triangles are, quote, special is because we know that every time the hypotenuse is just equal to one of the legs times the square root of 2. And if I wanted to get that in decimal form, Just say, what's the square root of 2? It's 1.41. Multiply that by 8. So the length of the hypotenuse in this small triangle that I've drawn would be, what was that, like 11.3. Okay, just to summarize one more time what we have here with 45, 45, 90 triangles. The legs are the same length. The hypotenuse is equal to the length of the legs times square root of 2. Okay, now we're going to talk about 30, 60, 90 triangles. This is another type of special right triangle where we know what the relationship between the three sides is without even using the Pythagorean theorem. It's faster than using the Pythagorean theorem. Okay, so let's start with this triangle that I have right here, and let's say it's equilateral. All right, so each of these angles is going to be the same, and in order for that to work, they would all have to be 60 degrees. Right? If they're all going to be the same, they all have to add up to 180. 60 plus 60 plus 60 is 180. That's an equilateral triangle. And then let's say that each of its sides, let's say we don't know what number it is, but let's say each of the sides is equal to 2x. 2 times some number. Right? Each side is 2x inches or feet or whatever units long. Okay? Equilateral triangles have all three the same angles, all three sides are the same also. Okay, now let's say we bisect this angle at the top with a line that's perpendicular to the base of the triangle. I start up here and I draw a perpendicular bisector to the base of the triangle. What have I just done? Well, I've taken an equilateral triangle where all sides are the same and all angles are the same, and I've created two 30, 60, 90 triangles. Well, obviously here's the 60. Where do I get the 90 and this 30 from? Well, obviously the 90 is going to come from right here, right? And the way I know that is because I made sure that when I drew this green line bisecting this angle at the top, that it was perpendicular to the line at the bottom. And when two lines are perpendicular, it means they meet at a right angle. So I have the 60 and the 90. Where do I get the 30 from? Well, I get the 30 from up here because I bisected a 60-degree angle. Okay, well, why did I bother to do that? Here's why. If this side right here is 2x and this side down here is 2x, and I've just split this 2x side in half, what I know is that this part of the base, this half of the base right here, is just going to be x units long, right? Because this part over here would also be x. Those two would have to add up to this 2x right here. So I already know that the shortest side of a 30, 60, 90 triangle is half as long as the hypotenuse of a 30, 60, 90 triangle. So now let's figure out what the other leg of this 30, 60, 90 triangle is. I've already kind of started doing it over here. Again, we would start with the Pythagorean theorem, a squared plus b squared equals c squared. And what I've done is, if I'm going to call this side at the bottom, I'm going to call this A, I'll call this B, and then obviously the 2x would be my C, right, because it's the hypotenuse. If I start substituting things in, A, remember, was just x, so I'd have x squared. B is the one I don't know yet, so I'm just going to call it b squared. And then C is this 2x right here, right? So I've just substituted things in to the Pythagorean theorem that I know about my triangle that I'm working with over here. So I have x squared plus b squared equals 2x squared. X squared plus b squared stays the same for now. When I square 2x, that's like saying 2x times 2x. I have to square the two constants, so 2 squared is 4, and then x squared is just x squared. That's how I got here, right? 2x squared means 2x times 2x, which gives me 4x squared. All right, so if I want to combine like terms here, the reason I would want to do that is because I eventually want to get to where I just have b by itself, right? I want to know what this is equal to. So I'm going to subtract an x squared from both sides. Oops. Those go away. B squared equals. I have 4x squared, and then I lose one of the x squareds. That would leave me with 3x squared. And now I'm back to where I have b squared instead of just b, right? I want to get rid of this squared And the way I do that is to take the square root. If I take the square root of the left side, I got to take the square root of the right side. The square root of b squared is just b, which is what I was going for. On the right side, I would have the square root of x squared times the square root of 3. Right? I just broke apart the radicand here. The square root of x squared is just x, so b is equal to x times the square root of 3. What this means is that when I have a 30, 60, 90 triangle, we already know that the shortest side, the shortest leg, is just half as long as the hypotenuse. B, this other side, is equal to x times the square root of 3. So this shortest side times the square root of 3. So the hypotenuse is twice as long, or I guess to make this make sense grammatically, I'd say 2 times as long as the shortest leg, and the shortest leg is half as long as the hypotenuse. If I want to get from the hypotenuse to the middle, or the medium-sized leg, I would just cut it in half and then multiply it by the square root of 3. So I didn't leave enough room on the last page, but this number 3 here follows up from the last page. The other leg, or the medium leg, is equal to the shortest side times the square root of 3. Okay, now a couple of examples. And I think after you do a couple of these, it'll make more sense. Okay, 2a right here. This is going to be a 45, 45, 90, right? Because this side's x and that side's x. It tells me that I have an isosceles triangle. So this angle right here and this angle right here would both have to be the same, which means they would both have to be 45. Okay, so the formula for finding the hypotenuse of a 45, 45, 90 triangle is the hypotenuse is equal to L times the square root of 2. All right, so what do I have here? Well, I don't have either of the legs, but I do have the hypotenuse, right? So if I'm going to use this formula right here, I'm going to plug in this 5 times the square root of 2 right here for h. So 5 square root of 2 equals the legs, which in this case are both x, times the square root of 2. All right, so the hypotenuse, this right here, is equal to the legs, which in this case are x, times the square root of 2. And the way I know that is from the previous, or 2 pages ago, where we figured out that when I have a 45, 45, 90 triangle, the hypotenuse is always equal to the legs times the square root of 2. All right, well, how do I solve this equation? I want to get x by itself. I want to get that by itself, which means I have to get rid of this square root of 2 somehow. Since I'm multiplying x by the square root of 2 right here, I have to divide by the square root of 2. Okay, well, what happens when I do that? It's really pretty easy. These two square roots of 2 cancel each other out. So on one side, I would just have x. Over here, these two square roots of 2 cancel each other out, which just leaves 5. So that means that both of these legs up here are just 5. 2b, what do I have here? Well, I have the hypotenuse is 18. And I know that whenever I have a hypotenuse, it's equal to the legs, which in this case are x, times the square root of 2. Same thing here. I have to do the same thing here as I did back here. I just have to divide both sides by the square root of 2. This one's not going to be quite as simple, but it's still not bad. Those two cancel each other out, leaves me with just x being equal to 18 divided by the square root of 2. Remember from the review page, though, we don't ever want to just leave a radical in the denominator of a fraction. It's just one of those things that you're not allowed to do in math. What we do then is we just square the denominator, right? But if I square the denominator, I have to do this, multiply the numerator by the same number. When I square a radical, I just get the radicand, right? In other words, the square root of 2 times the square root of 2 is just 2. Up top, I would have 18 times the square root of 2. Now I can simplify, right? Since I could do 18 divided by 2 to simplify this a little bit more, right? The square root of 2 is going to be left alone. It's going to stay up here. But 18 divided by 2, actually it's not going to be a fraction after this. 18 divided by 2 is 9 times the square root of 2. That would be my answer. Okay, this one I'm going to do the same thing, but no picture. No picture. So I'm going to draw it myself. It doesn't have to be perfect. It just has to be enough for me to see what's happening. So I'm going to draw an approximation of a 45, 45, 90 triangle because that's what it says I'm dealing with here. Hypotenuse has a length of 11, and I'm just going to call the two legs x. I know they're the same. So again, I know the hypotenuse is equal to the legs times the square root of 2. I'm going to divide both sides by the square root of 2, right? Because I want to get x by itself. So x is going to be equal to 11 over the square root of 2. I don't ever want to leave a fraction with a radical in the denominator, so I multiply both sides, or sorry, the numerator and the denominator of the fraction by the square root of 2. When I do that, the bottom just becomes 2. Up top I have 11 times the square root of 2. I could leave it like this, or I could put it in decimal form, but if you want to just leave it like that, that's fine. All right, now a few examples with 30, 60, 90 triangles. What I'm going to do on this one, 3A, is I'm going to redraw this triangle so that it looks like the one I did the example with before. Right, so here's my 90-degree angle, here's my 30, here's my 60. And then I'm going to label the sides with what it gave me. What it wants me to do is figure out what x and y are equal to. So what I know from before is that the hypotenuse is just twice as big as the shortest side, and then this third side is just equal to the shortest side times the square root of 3. That's the relationship between the lengths of the sides in any 30, 60, 90 triangle. But then what information does it give me about those sides? Well, it tells me that the hypotenuse right here, one across from the right angle, is equal to y. It just leaves this one, the shortest side, as x, and then it tells me that the middle side back here is equal to 12. Okay, the reason I'm solving the problem like this is because it kind of tells me where to start. Look at these three equations. Which one is something I could actually solve to figure out what number of variables equal to? Can I do it with this one? No, because those aren't like terms. I can't really combine them yet. X equals x, that's not going to tell me what x is equal to. But if I look over here, there's something I can do to actually figure out a number that x is equal to. So I'm going to start back here. So I'm going to say 12 equals x times the square root of 3. If I want to get x by itself, I'm going to divide both sides by the square root of 3. So x is going to be 12 over the square root of 3. I don't want to leave a radical in the bottom of a fraction, so I'm going to multiply. And that's going to give me 12 times the square root of 3 over 3. I can reduce, because 12 divided by 3 is 4, so x is 4 times the square root of 3. All right, so now I know what x is equal to. Right, one of the variables I'm solving for here is x, and I just figured that out. X is equal to 4 times the square root of 3. The other variable I want to know is y. This one's going to be easy, because I know that anytime I figure out the shortest side of a 30, 60, 90 triangle, the hypotenuse is just twice as big as that, or 2 times that. So if I want to know what y is equal to, y is just equal to 2 times whatever x is. Right? I just took x, put it in there. I'm going to multiply it by 2. And 2 times 4 times the square root of 3 would just be 2 times 4 is 8. So 8 times the square root of 3. And that's basically it for 3a. 3b, I'm going to do the same thing. I know that 2x is the hypotenuse. Y over here is just x times the square root of 3, and x is just x. Which one of these three equations can I actually solve to figure out what a variable is equal to? Here I have two variables, can't do it. X equals x tells me nothing. 2x equals 10, that I can solve for. So I'm going to kind of draw a line to divide the last problem from this one. I'm going to make a box over here with what I want to know. I want to know what x is. I want to know what y is. 2x equals 10. I can solve that for x really easily with one step. So x is going to be equal to 5. Okay, so I know that this side right here is 10. That means x is half of that. So this side down here would just be 5. Now I want to know what y is. Well, y is equal to x times the square root of 3. If I substitute in a 5 for x, I get y. And I could turn that into a decimal if I want, but if I'm feeling lazy, I just stop right there and I say y is just 5 times the square root of 3. 3c, same thing. The hypotenuse, the longest side, is just equal to 2x. The shortest side is just x. And then the side in between is x times the square root of 3. I set these equations up so that I can see what I want to solve for. Okay. Here I have an equation that doesn't seem to make any sense to start with, but it will. I can't tell you what number x is equal to just by looking at that, though. So I'm going to skip that. Same thing here. Doesn't really give me anything to solve for. 21 equals x. That one's pretty easy. I don't even have to solve for anything. X is just going to be 21. What that means is that if this side is 21, this one up here is 2 times that, right? Remember back to this triangle. If that one is x, the hypotenuse is 2x. So whatever this one is, I just double it to figure out how long the hypotenuse is. So in this problem, x is 21 times 2, which is 42. The only other variable I have here is y, once again. Y is equal to whatever this shortest side is times the square root of 3. So it's just going to be 21 times the square root of 3. I'm going to solve this one over again. So write this down or pause the video because I'm going to erase. I want to solve this over again in case it confused you by me having 2 different x's that I was talking about here. So in any 30, 60, 90 triangle, the relationship between the shortest side and the longest side is that this one, the shortest side, multiplied by 2 is the hypotenuse. So again, whatever this shortest side is, times 2 is the hypotenuse. So if this shortest side is 21, x would be equal to 2 times 21. 2 times 21 is 42. That's where I got this number right here. Okay, the other thing I know about 30, 60, 90 triangles is that the middle side, the medium side, which they're calling y on this one, is just equal to the shortest side, 21 here, times the square root of 3. And I could turn that into a decimal if I want, or I can just leave it how it is. That's how I got the answers here. Okay, last example for part 3 of Unit 8. And I know this video has been really long. Sorry about that. Promise this is the last one. Okay, it says an equilateral triangle has an altitude length of 18 feet. So let's draw an equilateral triangle. Remember, that's one where all 3 sides and all 3 angles are the same. So there's my rough approximation of an equilateral triangle, and it says it has an altitude that's 18 feet. So remember, an altitude is when I start at a vertex and I draw a perpendicular line to the opposite side. And so it tells me that this line right here is 18 feet. What does it want to know? It says determine the length of a side of the triangle. So it wants to know, like, how long is this side down here? Okay. Well, the way we're going to solve this, obviously, is to sort of think of this as 2 30, 60, 90 triangles, right? This part over here, that right there is going to be my x. Going back to the way I first introduced 30, 60, 90 triangles, this would be 2x. And this 18, this side that's 18, this altitude is just the second longest side of the triangle, is x times the square root of 3. Okay, so I can look at this here, 18 equals x times the square root of 3. That's going to let me know what x is equal to. Okay, I'm going to solve this equation for x. We've been doing this now. First step always is to divide the radical away from x so that you get x by itself. So I'm going to have 18 over the square root of 3. Then I'm going to multiply the denominator and numerator by the radical in the denominator. That's going to leave me with x being equal to 18 times the square root of 3 over 3. Then I look at the coefficient of the radical in the numerator and the denominator. 18 and 3, can I reduce? In other words, can I do 18 divided by 3 and get a whole number? Yes, I can. So x, after all that, would be equal to 18 divided by 3, which is 6 times the square root of 3. Okay? So this down here, this side down here, is 6 times the square root of 3. It wants to know one full side of the triangle, though. In other words, it wants to know that distance. I have half of that right here, right? So if I want to know the length of one full side of the triangle, I would need another 6 times the square root of 3 over here. So I would have 6 times the square root of 3 plus another 6 times the square root of 3, or I could say 2 times 6 times the square root of 3, which would just be 12 times the square root of 3. And that would be my answer. And if I want to convert that to a decimal, I haven't really done this yet. You could probably figure it out. 12 times the square root of 3, if I want that as a number that's easier to kind of grasp, I tend to prefer to put things in decimals. So what that just, all that means is 12 times, come to the calculator, square root of 3 is 1, let's just call it 1.73. So 12 times 1.73. So about 20.76. So the length of a triangle, an equilateral triangle with an altitude of 18, is about 21.